Welcome, everyone. My name is Helen. This is the Confidential Computing in Genomics webinar hosted by the Confidential Computing Consortium. We are a community focused on open source license projects, securing data in use, and accelerating the adoption of confidential computing through open collaboration. Everyone is welcome. We are a transparent and collaborative community. Feel free to ask your questions in the chat at any time during the presentation, and we will get to them. This webinar will be available on YouTube on demand later. Okay, so now I'll hand it over to Ruslan, who is the COO of GENXT, to introduce our speakers in the webinar.
Yeah, thanks, Helen. Let me show my screen, share my screen, and show a presentation. Yeah, let me know if you see it.
We see it.
Yeah?
Yep.
Yep. Thanks, Helen. It is a pleasure to be speaking today. And hi, everyone. My name is Ruslan, and I'm the co-founder and CEO of GENXT. And here's also our team, Stas, the CEO, Pavel, CTO, and Mariam, our business development manager. Yeah, I want to say that I'm excited to talk today about our solution as part of a webinar for consortium members who actually understand what is this technology. Most of the time we find ourselves doing the opposite, explaining why everyone in life sciences should implement confidential computing in their systems. And thank you for this opportunity. So, agenda for today's webinar is to give a quick overview of our company and the market we address, explain the problems we deal with, also present our first application from both technical and commercial perspectives. We want to discuss the standards we implement, and finally highlight our future use cases. Starting with our company, GENXT is a deep tech startup that develops solutions for multi-party data analysis in genomics and precision medicine without disclosing data, without disclosing machine learning models or computational results. Our solutions are tailored for personal genomics companies, public biobanks, and pharmaceutical stakeholders. Having more than 10 years of experience in personal genomics and software development, our team came up with an idea of our solution in 2018 when we discovered confidential computing technology. The technology wasn't widely available at the time, but essentially it was a missing piece for the introduction of data collaboration solutions in genomics, given the highly sensitive nature of data. Later, we completed the Biocity Business Acceleration Program and founded GENXT in the UK in 2019, becoming confidential computing early adopters in genomics. And since 2021, we reside at the Wellcome Genome Campus in Cambridge, the home of the foremost organizations in genomics and computational biology, such as Elixir Europe, ABI, Sanger Institute, Genomics England, Illumina, and others. We also participated in the Microsoft for Startups program and using Microsoft Azure infrastructure and the SCOM framework. Our team has built a protocol for multi-stakeholder analysis of distributed genomic data that ensures full confidentiality and integrity of data in code using data processing. Let's talk about the market. It became obvious that genomics is one of the key drivers in the realization of precision medicine. This sector is still in its very beginning, but is developing rapidly. We already know that genomic data increases drug approval by more than twofold. And we know that there are more than 250 personal genomics companies and more than 120 public biobanks. And there are more than 50 million direct-to-consumer genetics tests sold. However, given the growing awareness of data sensitivity, most genomic data remains siloed in isolated data sets, fragmenting research efforts to generate new knowledge from this data, as the demand of AI applications on diverse genomic data increases. And the industry, it is obvious that industry requires secure solutions for collaborative computing. And confidential computing actually plays a crucial role in helping us to solve this problem, as it allows us to achieve basically two things. First, it enables the execution of software of programs that handle sensitive data in enclaves, in these isolated encrypted areas of memory. And second, it provides remote attestation of these enclaves, allowing us to verify that we are communicating with trusted, tested software while exchanging the data. And by utilizing these features in our solution, we ensure that data always stays encrypted and undisclosed. This is crucial for us. This facilitates regulatory compliance in different jurisdictions and solve many technical problems. It also supports fast processing of high volume data sets without a significant computational overhead, while preserving data security, of course. And it is especially important for machine learning applications because it handles a lot of data. And it also provides interoperability with other platforms and ecosystems in the field, because we implement the Global Alliance for Genomic and Health frameworks and standards. I'll come back to this a bit later. About use cases, how we use the technology, what we do. Our first use case addresses direct-to-consumer personal genomics. We developed cross-database DNA matching that allows personal genomics companies to match DNA of their customers across each other's databases and identify DNA relatives without genomic data disclosure among participants. As I said, our team has more than 10 years of experience in the personal genetics market, and we saw that DNA matching is one of the most popular direct-to-consumer genetic testing services among companies. And together with Ancestry prediction services, it represents more than 50% of 50 million direct-to-consumer genetic tests sold worldwide since mid-2000, since the emergence of this market. Yeah, but it also has some limitations. These days, product is delivered by matching customers within a local database of one company. As was said, there are more than 250 such companies worldwide, and each may contain DNA relatives for the user. Moreover, most companies do not offer DNA matching at all due to limited database sizes. To be honest, they just can't find a sufficient number of matches for their users. That's why they do not offer such a service. Coming back to our solution, our cross-database DNA matching service aims to overcome these issues as it delivers great value to customers, obviously, and enhance DNA matching by connecting with personal genomics companies around the world, by connecting your users with other companies and with users in other companies' databases. Second, it boosts the number of premium subscribers by adding cross-database DNA matching as a new feature to companies that already offer DNA matching searches. And third, it creates an opportunity for new business-to-business revenue streams by letting companies search for DNA matches in your database. Now, moving to more technical side, I would like to describe the key features and walk you through our solution architecture and workflow. So first, personal genomics companies can only see matching results, and cannot access genetic data of other companies. Our company as a service provider and can only monitor task statuses. We don't have any access to data or to results of matching. Second, there is no centralization or obligations for participants. Personal genomics companies control their own policies for collaboration. They control it independently. They can choose permissions for each partner in the network. They can decide if they want to work with this company or not. Third, personal genomics companies exchange matched customers with the personal information that customers agreed to disclose with their DNA relatives before initiating the network search. So they sign the consent if they want to share some personal information with their potential relatives. And finally, all interactions between partners in the network are peer-to-peer connections. Again, no man in the middle between companies. They exchange data peer-to-peer in a peer-to-peer way. This is an overview of our architecture, and what's important that GENXT solution is built as a mediated peer-to-peer network that includes independent nodes. And it is mediated because we have mediator, the entity that helps them to find each other. I'll come back to this a bit later. Nodes. Nodes are the confidential computing instances hosted by personal genomics companies on-premise or in cloud. A personal genomics company deploys this software from the trusted repository maintained by a third-party international recognized cybersecurity provider. A node sends and receives data from other nodes using its secure storage and process data in the worker service. And we understand that the node software handles highly sensitive data, right? And making it important for all participants to be aware of the software we use for that. The software that your partner uses in order to process your information, your data of your users. As I said earlier, we can attest enclaves and ensure that nodes run, that nodes can only run tested and trusted software. And to have confidence in this software at all times, we deploy all updates from this trusted repository, which is accessible to all participants and contains tested and verified software. This code, as I said, is audited, tested, and signed by a third-party international cybersecurity provider. The mediator. The mediator hosted is it is a service hosted by GENXT. It provides network discovery service, attestation service, authorization service, and the task queue. And as I mentioned, the mediator does not see, store, transmit, or access genomic data or personal information or the results of matching. It only gives you access to the network and monitor the activity of your node. That's it. Let's talk about how it actually works. In order to match users from two databases, we should merge them and run some bioinformatics pipeline against this new merged dataset. But how can we do that without disclosing the data? Because obviously we run this pipeline on some machine. As it was said during the matching process, nodes communicate directly with each other, and the worker used for computations is deployed in the trusted execution environment. And node initiating the task performs remote attestation of the partner's node and remote attestation of its enclave before establishing TLS connection for data transfer. After the data transferred, second node merges two data sets inside the protected environment, runs the pipeline for relative detection, and sends back the results. And as you can see, mediator or any third party does not interfere in this process. And more importantly, that during the whole cycle of workflow, data stays encrypted. Yeah, and let me now describe a workflow on the network scale. So imagine we have node 1 and node 2 that want to match their users, and node 1 initiates the relative search by submitting a task for node 2 to the task queue on the mediator. After that, mediator checks if this request matches node 2 policies. And if yes, the second node receives a task and checks its permissions again. So now, node 2 has this task in their internal queue. And as we know, workers are deployed in the trusted execution environments and can attest each other's software using remote attestation process. So the first node now wants to attest the node 2 enclave in order to it want to be sure that it is a genuine software and it is a trusted software. And when node 1 understands that it is safe to share data with another enclave in the network, it opens access to the data set with the list of users, with a list of user IDs actually, and their genomic records. And using secure storage, which is also deployed in trust execution environment, the second node can now download data, process it, and send back the results to the exact same place in secure storage. About the results of this cross-database linear relatives matching, the first node, in the end, the first node receives a file where all users from both databases are matched with each other. Each pair of users who have shared parts of genome called IVD segments is placed in a new line with user IDs from both databases with kinship degree and portion of personal information. As I said, user can consent to share some of this information with their relatives. It can be name, sex, age, or any contact information, for instance. Infrastructure, how we run it. I actually don't want to spend too much time on this slide, but what is important in this, that we use Azure Cloud as a provider of confidential virtual machines. This Microsoft product supports the latest Intel CPUs, and this is a requirement for this product to be run on Intel SGX instances, Intel SGX enabled instances. This infrastructure was developed for smaller companies, and we asked them to use Azure, but we understand at the same time, we understand that bigger companies actually have more resources and bigger data sets, and they may want to install the software on premise. This is also possible, but as I said, we have some hardware requirements. The hardware should be Intel SGX compatible. A couple of words about the software for DNA relatives matching we use in workers. GENXT has developed Grape, the world's first open source end-to-end pipeline for relatedness detection, which can estimate close and distant degrees of kinship. It combines necessary pre-processing steps and some comprehensive data quality control to make it work with real-world data sets. Grape is an open source project. Feel free to check it out. And it was presented at the Bioinformatics open source conference a couple of years ago and published as a software article tool in F1000 Research Journal. Grape is also available on at Azure Marketplace with our team's support. Another important thing that our solution actually endorses standards developed by the Global Alliance for Genomics and Health that unites more than 500 leading organizations in genomics and healthcare. GENXT is a general member and contributor to the G4GH. We use different standards and APIs in our system. Yeah, and the described use case, we run Grape software for relatives detection, but it is also possible to run other applications and pipelines inside trust execution environments, right? So this opens the opportunity to offer other products to the industry. First, other types of tasks for confidential cross-database data analysis, or a service for confidential machine learning model training on one or several data sets without disclosing the matching the machine learning models or data it trained on, or the code of the model. Our team is working on a service for federated ancestry prediction, and we also released a scientific paper on this. And another application we work on is a solution for confidential machine learning model and software tool licensing. It allows companies to rent their pre-trained models or software tools to their clients, installing them into the client's infrastructure without losing control over it. We also work on another projects. We aim actually to set a new standard for building trusted research environments based on confidential computing. This will facilitate the connection of siloed databases from public and private biobanks with research institutions and software vendors, allowing them all to leverage each other's data and software without disclosure. Yeah, that's basically it. Thanks for your time, and thank you again for the opportunity to tell you about our ideas and our products. And I'm happy to answer questions if you have something. Yeah, I know actually. Yeah.
Yeah, so I was going to ask the questions while we're waiting for questions. So now does Ruslan, please do finish.
Yeah, I just wanted to say that I know that we have a list of frequently asked questions from our clients. We can continue with that.
Yeah, I was just going to get to that. So yes, this is a set of questions that we usually get asked by potential clients or other confidential computing adopters or investors. They concern both the cross-database DNA matching case and overall about our concept. So the first one is, what data are we expecting as inputs from a personal genomics company in order to engage in cross-database DNA matching?
Mm-hmm. Yeah. The Grape's pipeline requires a single multi-sample DCF file as an input. IBD segments detection workflows of the pipeline can work with both phased and unphased data, and as real-world data sets are often heterogeneous and inconsistent, Grape has some data preprocessing and quality control options. It has a modular architecture. It allows switching between different tools and adjusting tools and its parameters for better control of precision and recall levels. Yeah.
Mm-hmm. And the second one would be, do you work with encrypted data?
Yeah, actually, yes. Yeah, the system employs the G4GH approved Crypt4GH encryption standard for sending data between the network nodes, providing an encryption keys for trusted software instances executed in trusted execution environments, and these keys only available to these trusted instances. The instance decrypt data, as I said, it decrypts data inside enclave, inside its isolated environment for one-time processing, and then eliminates the data. So in fact, the data remains encrypted at all stages, and actually can't be viewed or copied or modified by anyone, including the system administrator of receiving node. That's thanks to confidential computing, it is possible.
And now with respect to personal genomics companies, so they have a different number of genomic samples in their databases ranging from 10,000 to millions. The question is, do you work with one genomic sample at a time? Can you match the entire data set or one record at the time?
Yeah, we can use your whole data set. The system actually splits the entire background data set. We call background data set your data connected to the network, and process it step by step, matching with a batch of data from another company. Yeah, so answering your question, yes, we can use the whole data set.
And assuming that, oh, I think there is a question in the pop-up window. Let's address that one, Ruslan, and then while others think about other questions, we can get back to mine.
Yeah, Drasko asking, can you please deep dive in trust execution environments, which is are using SGX, SAV, TDX, Agentic Multi-Party Attestation? Do you use Microsoft Azure service, or you're implementing your own? Yeah, thank you for this question. Yeah, this is actually a good question. For cross-database relatives matching, we deploy Intel SGX enabled instances. So we use SGX enclaves, and we use the SCOAN framework for enclave management and for remote attestation. If you're familiar with this framework, it's brilliant. You have to try it. Yeah. So I hope this answered your question. Oh, you also asked if there a whole database in trust execution. Yeah, we actually send data sets as VCF files. It's just comma separated files with the tables and some numbers. So we share a file, and the whole file is encrypted, and we load it to the memory by batches, like small portions. But it is encrypted at all times. We save it in encrypted file system. So only trust execution environment, only the software we run inside the enclave can access it, decrypt it, and use it in runtime.
I think my question actually is, my next question was very relevant to this and the previous question. So assuming that you did match the data set, companies get new clients, new samples. So the question is, how do we deal with a growing database? Let's say a company has 3 million genomic samples and then receives 10,000 more in 1 month's time. So what do you do next?
Yeah, if you want to initiate the network search, you can send just new samples to other nodes, right? Because you obviously have all the matches for your old users. And you can do that by using our node API. And as you add new samples to the background data set, that will be matched with another company's data set, and is connected to your node. The whole updated data set obviously will be a part of future searches, right? So yeah, you can send your new users to the network, or you can just update your existing data set and use it. Actually, you also can send just one record in the network if you need it.
Thank you. And I think the final question is, and Ruslan already touched upon it when we described a number of cases that are possible, but I think it would make sense to dive into the other application for personal genomics for another bestseller along DNA matching, which is ancestry prediction. We've been also working on that a little bit. So Ruslan, could you please kindly give an overview?
Yeah, sure. Yeah, as I said earlier, besides DNA matching, nodes could provide machine learning models training in federated setting, in federated environment. Node can train model on some distributed data located in several data banks. It could be used for training, for instance, ancestry prediction models. Another bestseller of this market. It can be trained on a number of distributed reference panels owned by different companies or different public biobanks, for instance. And in this scenario, the protocol that we developed protects not only data but code and trained models, and its integrity and confidentiality. In other words, the model's code and trained models are protected from being disclosed, from being stalled. Still, we studied the applicability of federated learning on genomic data. We studied this in two scenarios, actually: phenotype prediction on the UK Biobank data and ancestry prediction on the 1000 Genomes Project data. So this is one of the scenarios how we can use our protocol, our platform.
Thank you. There are no more questions from my side. Thank you very much.
Yeah, thanks, Marianne. Yeah.
All right. If there are no more audience questions, we will close the webinar here. Thank you, Ruslan, for this great presentation on confidential computing and genomics. We will have this webinar on YouTube later for all to view later. So have a great day, everyone.
Yeah, thanks, Helen.
Thank you.
Thank you.
Thank you. Bye-bye.
Bye.